Your questions. Do you have any specific question that you would like us to discuss? Finish negotiating?
Glass lotlarda ya da herhangi lotlarda dairesel şeklinde olan şu tarz lotlardan bahsediyorum. Bunları seçerken ilkelerin sınırlarını oradaki açılara göre alıyoruz da yani daire 2'de 3 gibi düşünmemiz gerekiyor mu bu sorularda? Mesela şurada
Let's look at the example.
Induction demiş.
Now, in this question, you have the xy axis, and then you have an arc. Just a segment of a circle. This is 60 degrees, this is 60 degrees. The radius is r, and the total charge is q. And the charge is uniformly distributed. And this is the point C. Okay, in the first part, you are required to find Ex. So how would you proceed? How? Why? So you say that we should first, we divide this into very small segments. This is not a sphere, this is a circle. We just take one of them, let's say this one. It has a charge dq. What is the magnitude of the electric field it creates? Sağlıklı yaşa. 1/4πε0 dq over r squared. This is the magnitude. And at this point it is, let's say, in this direction. It makes, let's say, it makes an angle theta. So what is the contribution to the x component? One over 4πε0 dq over r squared times cosine theta. And the total x component would be just the sum of the contributions to the x components. And this is 1/4πε0 dq over r squared times cosine theta. Well, also keep in mind that r squared is also a constant. So this is actually, I can also take it out. 1/4πε0, 1/r squared times dq times cosine theta. Now we have to somehow write dq as a function of theta, or the increments in theta. Now if you go back to this segment, let's say that segment, I can just imagine it as the arc corresponding to this very small angle theta. And what is the arc length? It's just r times d theta. The charge, lambda times dl, or dl is r d theta, and lambda is just q over 3. No, sorry, not q over 3. Q over the total length. What is the total length of this arc? 2 pi r is the total circumference. But this is just a part of that circumference, not the whole thing. And this is just 1/3 of the total ring, so 2 pi r over 3. The total charge is distributed over a length of 2 pi r over 3. This is the charge per unit length, and this is the length that we are considering. So this is equal to, r's will cancel. This is equal to 3 over 2 pi q d theta. Now let's substitute it back. Ax is equal to 1 over 4 pi epsilon 0, 1 over r squared. Now dq is 3 over 2 pi q times d theta times cosine theta. Or let's say 3 over 8 pi squared epsilon 0 q over r squared d theta cosine theta. Now the next thing is we have to determine the ranges of theta. What is the lower limit? What is the upper limit? So first of all, what is the range of theta? Well, if let's say pi over 2 or pi over 3. So it should definitely go from minus pi over 3 to pi over 3. But should it start from the larger one and go to the smaller one, or start from the smaller one and go to the larger one? You see, this ring, this arc corresponds to theta between minus pi over 3 and pi over 3. That is for sure. But it doesn't, for an integral, the lower limit doesn't have to be always the smaller one. You can go both ways. And the difference will make a sign difference in your result. So in this case, look at this relation. We define dl to be positive. It's the length. It's a positive number. So d theta also has to be positive. But d theta is nothing but the change in theta as we go from one segment to the other segment. So that tells me that I should start from the small value of theta and go to the larger value of theta. So the smaller value is minus pi thirds. The larger value is plus pi thirds. So that is how I determine the limits, the order of the limits. Well, let's evaluate the integral. This is 3 over 8 pi squared epsilon 0 q over r squared sine of theta when theta is equal to minus pi over 3 to pi over 3. What is sine of pi over 3? Root 3 over 2 minus root 3 over 2. So the final electric field is 3 root 3 over 8 pi squared epsilon 0 q over r squared. This is E of x. Always check your answers. You see, one thing that you have to be careful about is that, let's say, if the electric field, if q is positive, what should be the direction of the electric field? It will be in the positive x direction if q is positive. And if q is negative, it should be in the minus x direction. So if q is positive, Ex should be positive. If q is negative, then Ex should be negative. So to check, to make sure that you didn't make any sign mistake somewhere, just check. And if q is positive, everything else is positive, Ex is positive. So when we were determining the order of the limits of the integral, we didn't make a mistake. If we had made a mistake, then we would have a sign mistake over here. So, well, this is part A. Then you are asked to find the Ey. What is the y component of the electric field? Well, the y is it 0? So They cancel each other. So basically, if you have a dq over here, on the opposite side, you have another dq with exactly the same magnitude. And if you would draw the electric field line created by that dq, it will be in this direction. Well, when you sum these two vectors, you will see that the resultant vector is horizontal. They have the same x component, but the y components are just differ in sign. And since this rod is quite symmetrical, for every dq on the bottom, there is a dq on the positive y plane. So all of them will cancel. Ey is 0. If you explain, well, depends. You see, in the question they might ask you, well, show it explicitly by evaluating the integral. In that case, if you don't evaluate the integral, you will lose points. But if they just ask you what is Ey, and you explain your reasoning, there is the symmetry, and hence the Ey is 0, then that's fine. Well, if you want to evaluate this explicitly, you see the derivation when we were using Ex would be identical. The only difference would be, since we are taking the y component, we won't use the cosine of the theta, but we will use the sine of theta. So up to here, everything will be the same except replacing cosine with sine. But then, this integral is just 0. It is the integral is minus the cosine. Cosine pi third is equal to cosine minus pi third. So when you subtract, it just gives me 0. And then part C, it says that if you plate a plus Q charge at this point, well, let me draw fresh. This is R. And it says that at this point, now we place a plus Q charge. And then it says that when we put that plus Q charge over there, the electric field at origin at the point C is equal to 0. Well, let's see. We already have calculated the electric field of this arc. So the electric field of the arc, it has only an x component, and which we found as this expression. Well, the electric field of the point charge Q, they are both at the point C. What is the electric field of the charge Q? Somebody else? What is the electric field of the charge Q? 1 over 4 pi epsilon 0. Q over R squared. What is the direction? It's in the minus I direction. Now, what is the total electric field? Well, just sum them up. So let's say 1 over 4 pi epsilon 0. This is common. 1 over R squared is the same in all of them. I is the same in both of them. So what is left is we have 3 square root of 3 over 2 pi Q. This is from the first term, and minus Q from the second term, and we want this to be 0. So it tells us that Q, the small q, should be equal to 3 root 3 over 2 pi capital Q. And since capital Q is a positive charge, the small q should also be a positive charge. Does it make sense? The signs? Well, the plus charge will create an electric field pointing away from it. And so this charge should also create an electric field away from itself so that they will cancel. So at least definitely small q and capital Q should have the same sign so that they will cancel. Question? Pass it along. So we have a ring-shaped charge density. This is given as x, z, and y. The radius is r. And on the lower half, just on the lower half, it has a charge q uniformly distributed. So there is no charge density on the upper half of the ring, only on the lower half of the ring we have some charge density. Well, what is the linear charge density of the lower half? Q over the length is pi r, so this is the linear charge density. So we got 3 points. So let's see B. We are given this point P, and we are asked to calculate, it is at a distance x. We need to calculate Ex, Ey, and Ez. Well, tell me what is Ez. Well, Ez would be 0, because just imagine this ring. We have this point over here. If I take some segment over here, it will create an electric field in that direction. If I take another segment from here, it will create an electric field in this direction. So they will be kind of pointing like this. This component will cancel. So the sum will be some vector in that direction. Or let's see, let me try to sketch it. Let's assume we are looking straight from the top. If I look straight from the top, what I will see is I will just see a line charge density. I'm looking straight from the top. So this is the z-axis. This is the x-axis. And the y-axis is pointing towards you. Just imagine this as an arrow pointing towards you. This is my y-axis. Now, if I take this segment, it will create an electric field in this direction. Well, on the opposite side, there is a symmetrical segment with the same charge density. It will create an electric field pointing in this direction. When I sum them up, this is what I will see. So no component in the z direction. By the way, that blue arrow is not in the x direction. Because I'm looking straight from the top. I don't see any y components. Yes, when I look straight from the top, it looks as if it is along the x-axis. But keep in mind that I'm not seeing the y component, so it might still have some y component. The only thing I know is that it doesn't have any z component. So Ez is already 0. Now let's try to calculate the other components. Well, along with this figure, I will also draw another figure which is straight from the side. This is from the side. This is the x-axis. This is the y-axis. And now this is the z-axis looking at you. Now, looking straight from this side, this segment and this segment will in fact overlap. They basically have the same y component. So it is this segment over here. Let's say this segment has a charge dq, this has a charge dq, this has a charge dq. But there, I essentially have two charges dq, one closer to you, one further away from you. And if I would plot these red and blue curves, blue arrows, this is my point P. This is my red arrow. And this is exactly the same, the blue arrow. So in this picture, there are two vectors pointing like this. You just see one behind the other one. In this picture, you just see them like this. You only see two arrows. Now let's see. I need to define some angles now. Let me write first the magnitudes. Then we will deal with the angles. dE created by this one. Let me call this distance for the time being L. It is the same throughout the ring, so I will just call it L. What is dE? One over 4 pi epsilon 0 dq over L squared. So, and similarly for the red part. Now let me define some angles. Let me go back to the three-dimensional picture here. So let's say that at the point P, if I have any vector, this is just an arbitrary vector, not necessarily the electric field or dE of anything. An arbitrary vector. I can take the projection on the x-axis. So that I can do, let's say this is a vector A. Ax will be just A times, if I call this angle theta, A times cosine theta. It's just the angle that the A vector makes with the x-axis. Then at the same point, let me draw the z-axis and the y-axis. I can imagine let's say the shadow or the projection on the xy plane. So let me just draw a line parallel to the x-axis from the tip of A. So let's say it crosses the xy axis at this point, at that point. Now I will define another angle with the z-axis. Let me call it phi. No, sorry, not phi. So AZ will be A times sine theta, which is nothing but this length You see, this length is actually here. Let me also put it over there. This is a right angle. So there I have a right triangle, somewhat, you see it like this. It's inclined towards you. So this is a right angle. No, sorry. This is a right triangle with, here is the right angle. This angle is, this side has a length a cosine theta. This side has length a sine theta. It's the opposite side, opposite perpendicular side. So that is why this length is a sine theta. But then I need to take its projection on the z-axis. And to do that, I just draw a parallel line to the y-axis. It crosses the z-axis perpendicularly. Here there is also a perpendicular angle, a 90 degrees angle. This length is just this length multiplied by the cosine. And AY is A times sine theta, sine phi. So these are the three angles I have. Well, it's just like the spherical coordinates. The only difference is that instead of in spherical coordinates, the convention has it that the theta is the angle that a vector makes with the z-axis. In this case, it is the x-axis. Can you visualize this sketch? You see, just imagine this is my x-axis, this is the y-axis, this is x, this is y, and towards you is the z-axis. So I have this vector pointing in that direction. This is the angle theta. No, this is let's say this is the vector. This is the angle theta. So what I do is I just draw this perpendicular line. This angle over here is theta. So this length in the x direction is just the length of this hypotenuse multiplied by the cosine. This is the direction in the z-axis. Now this is my vector. My xy plane is this one. No, sorry, in this problem it's the yz plane. This is the yz plane. So this is the vector, this is the yz plane. So I take this perpendicular projection that's in this direction. So here there is also another right triangle. Let me put it like here there is another right triangle. This side is a sine theta. Now this is the projection on the yz plane. And the y-axis, no, the z-axis is towards you. This is the z-axis, this is the y-axis. This angle that this vector makes with the z-axis is what I call the phi. So the z component is just this length, which we said is a sine theta, multiplied by the cosine of this angle, cosine phi. So that's why I have the az. So if I take this, starting from this arbitrary vector, I first consider the projection on the z-axis. Then the remaining projection is on the the projection on the x-axis. Then the remaining part is in the yz plane. And I took this vector, the projection on the yz plane, took its projection on the z-axis and also on the y-axis. Those are the three components. Now let's apply this to this problem. The Ex, the x component of the electric field, is the magnitude multiplied by cosine theta. Well, let's calculate Ex. It's just the sum of all these contributions, which is the integral of 1 over 4 pi epsilon 0 dq over L squared times cosine theta. Now, which one of these are constants? We can just take out the constants. Well, 1 over 4 pi epsilon 0 is a constant. L squared is a constant. As we go from segment to segment, L squared doesn't change. Let's see what about cosine theta. Well, you see, cosine theta is the angle that the vector makes with the x-axis. You see, this is my ring over here. And the electric field is pointing away from my ring. So as as I'm tracing, summing the segments over the ring, this is my electric field also traces another arc. But along this arc, the angle I make with the z-axis doesn't change. So basically, the angle theta is constant. As I'm summing the contributions of all these segments, the electric field they create make the same angle with the x-axis, because all these segments make the same angle with the x-axis. So cosine theta is just a constant in our problem. And that constant, well, let's say if this is theta, well, let me draw it like this. This is theta, that is theta. Cosine of theta is just x over L. Remember, x is this distance over here, and this distance is L. So Ex is equal to 1 over 4 pi epsilon 0, 1 over L squared, x over L, this is cosine theta, times dq. But dq is nothing but sum of the charges of each one of the segments. Well, if I take the charges of each one of the segments and sum them up, I get the total charge. This is just q. So Ex is 1 over 4 pi epsilon 0, 1 over L cubed times x times q. Well, if you go back, so this length over here is r. This is x. So L is basically x squared plus r squared under the square root. You see, if you go back to this three-dimensional picture, this length is r, this length is x, and L is just the hypotenuse. So Ex is 1 over 4 pi epsilon 0, x over x squared plus r squared to the power 3/2 times q. Well, let's check whether this answer makes sense. Now, let's just imagine that this point P is very, very far away, almost infinitely far away. And you look at a very small ring from an infinite distance. Well, you will just see a point charge whose total charge is q. So the electric field should also be the electric field of a point charge if x is very, very large, much larger than r. Well, let's see. In the limit as x becomes much, much larger than r, well, just ignore r squared. So x squared plus r squared will be approximately just x squared. R squared will be very small. This will be 1 million. This will be, let's say, 1. You can just ignore it. So Ex becomes 1 over 4 pi epsilon 0, x over x squared to the power 3/2 q, which is 1 over 4 pi epsilon 0. Well, this is just x cubed. 1 over x squared q. X is your distance from the point charge. So your answer makes sense. Probably we didn't make any mistake. Well, let's look at okay, we already said that the z component was 0 because of the symmetry. We had already evaluated the x component. Now we need to evaluate the y component. Well, the y component, well, the derivation, what changes in the derivation is that here, instead of cosine theta, we have sine theta, sine phi. That's the only thing basically which changes. So Ey will be, let's say dEy is dE times sine theta, sine phi. dE, we had already evaluated it. 1 over 4 pi epsilon 0 dq over L squared. Sine theta Well, let's go back. We can write it down straight away. Here the cosine theta was x over L. Sine theta will be just r over L from that right triangle. R over L times sine phi. As we go from segment to segment, phi will change. So let's see, this is equal to 1 over 4 pi epsilon 0, r over L cubed, dq times sine phi. Or the total y component of the electric field will be 1 over 4 pi epsilon 0. You see, for every segment, r is the same, L cubed is the same, dq times sine phi. Now, how can we relate dq to phi? Well, let me plot it again. This is x, this is y, this is z. So the charge distribution is over here. Now let me look at straight from this side, from the x-axis. So the y will be up, z will be towards the left. And this is my charge distribution. Well, we just took a dq somewhere over here. This is just lambda times dl. dl is the length of that segment. If I connect that dq to the origin, phi is just this angle over here. That is what we call the phi. You see, when we were defining phi, for an arbitrary vector, we took the projection on the yz plane, but this is already the projection on the yz plane, and phi was defined as the angle it makes with the z-axis. So this length over here is just d phi. This angle, sorry, not the length. If you would just draw this wedge, that makes an angle d phi. So dl would be just r times d phi. So dq would be, and lambda, we had already written it down. It was q over pi r. This was r lambda. dl is r times d phi. These cancel, so this is q over pi times d phi. This is the charge of that very small ring. So Ey is 1 over 4 pi epsilon 0, r over L cubed, dq is q over pi, d phi times sine phi. Now the last thing is, so what are the limits of phi? Well, first of all, we already said that d phi is positive. We are increasing phi. But one little detail, let's say it is from minus pi to 0. So basically, usually you define, even in our conventions, you see here when we were defining phi, if theta is some number between, let's say, 0 and pi over 2, and if phi is some number between 0 and pi over 2, we define both AY and AZ to be positive. So we have to be consistent. So if phi is between 0 and pi over 2, then both AY and AZ should be positive. So basically phi between 0 and pi over 2 corresponds to this region over here. Below the z-axis, it's the minus phi region. So that's why it's minus pi to 0. And let's see, this is 1 over 4 pi epsilon 0, r over L cubed, q over pi. The integral of sine of phi is minus cosine phi from minus pi to 0. 1 over 4 pi epsilon 0, r over L cubed, q over pi. Cosine 0 is 1. And cosine of minus 1 cosine of minus pi is minus 1. This is 0. Okay, what was the mistake? Well, not the limits, but the z and the phi. You see, the z component is obtained by sine theta cosine phi, not sine theta sine phi. Oh, sorry. You see, what did I do? Is the z component is cosine phi, sine phi, okay. Well, when it is 0, there is a minus sign over here. Another minus sign is plus. Yes. So let me do it this way. Let me take that minus 1 out. Cosine 0 is 1. Cosine minus pi is minus 1. Okay. So it's just minus 1 over 4 pi epsilon 0 r q over pi L cubed times this is 2. Minus 1 over 2 pi squared epsilon 0 r q L cubed was x squared plus r squared under the square root, so it's the 3/2 power. Again, as usual, check the sign, at least. That's easy to check. If Q is a positive charge, you see I have some positive charge distribution over here. I'm looking at the electric field at this point. So what do you expect the direction of the electric field to be? It will be pointing somewhere in that direction. It's not horizontal. It won't be, okay. At this point, it won't be horizontal. But since these positive charges are below the plane, it will be pointing somewhat upwards. So what does that tell me? If I look at over here, EY should be positive. So I definitely made a sign mistake somewhere. Well, you see 0 to pi is just this region. You see z is 0 from this point. Z is 0 is this, phi is equal to 0 is here. As I increase phi, I just go around like this. I don't go like this. This is, you can say we go from pi to 2 pi or minus pi to 0. I'm sure about the limits. We made a sign mistake somewhere else. So let's go back first. Are we consistent with our definitions? The z-axis will be cosine phi and the y-axis will be sine phi. If this is my arbitrary vector, this is the phi angle, positive phi angle. That is correct. So let's look at over here. This is what we said, dEy is dE times sine theta times sine phi. Is this positive or negative? You see, sine theta, we are looking at a value of theta for which sine theta is positive. Do you agree? You see, this is the angle theta. So theta is, well, in any case, sine theta is always positive because theta is defined to be some number between 0 and pi. So sine theta is positive. Sine phi is negative. I'm saying that we are at the negative axis. So sine phi is negative. The reason why it is negative is that you see phi is that direction, but my electric field is pointing in the opposite direction. So that is why I have to include another minus sign over here. Mainly because my electric field is not pointing towards the charge, it is pointing away from the charge, and phi is the coordinate of my charge. Or another way of looking at it is, you see, let me not write it that way. You see, the phi angle, that segment creates an electric field in this direction. That is the direction of dE. And the phi angle it makes starts from 0 to pi. That's another way of looking at it. So since, you see, the positive phi angle is above the z-axis, the negative phi angle is below the z-axis. Okay, this charge is at the position of a negative phi axis, but the electric field is pointing in the positive phi direction. And the angle that the electric field makes with the z-axis basically starts from 0 to pi. That's why you're right. The limits are from 0 to pi. Cosine of pi is -1. There is another -1 over there, so it is a +1. And minus at phi is equal to 0, we have cosine phi is 1, minus cosine phi is -1. So at least we found one mistake by just looking at the signs. Well, two things that you have to always check: the signs, do they make sense, the directions? Secondly, the units. You see, the electric field always has the form of some charge divided by some distance squared. It should always have that form with 1 over 4 pi epsilon 0, 1 over epsilon 0. Well, let's see. There is the epsilon 0. There is the charge. And all this combination has the units of 1 over length squared. So it's probably correct. Now, whenever you are, when we go over your mistakes, when we are grading your exams, one of the common mistakes is sign mistakes, which in fact, if you just check your signs, you will discover that there's something wrong. The second kind of mistake is, for example, you just find the electric field an expression which looks like Q over R. Electric field doesn't have the charge over the distance units. It has the units of charge over distance squared. And if you would just check that, you would see that there's some mistake somewhere. And most of the time, it's just as you move from one step to the other step, you just forget some factor over there. Okay, so any questions on this solution? Well, this problem was hard to visualize. You have to be thinking three-dimensionally. But once you visualize it, well, the rest is kind of straightforward. So you see, okay, the y direction is kind of complicated. And the main complication is, again, let's go back. Let me plot this. Okay, this three-dimensional picture. That is the x-axis. This is the y-axis. This is the z-axis. And the ring is like this. Okay. So if I take this segment of the ring, it points in this direction. The electric field created by this segment points in that direction. Okay, let me just ignore the x component I have already calculated. So the electric field of this segment is pointing in this direction. And then I define, okay, the angle with the z-axis, this is the phi axis. Okay, so this angle, it creates an electric field whose magnitude in the x, y, z plane to be dE times the sine of theta times, if we project on the z-axis, okay, the cosine of this angle, cosine of that angle, cosine phi in the z-axis, and in the y-axis just the sine phi. Okay. Now, if you look at the, let's say, the z component, we said that, okay, this segment creates an electric field pointing in that direction, whose z component is pointing in that direction. This segment creates an electric field in that direction, whose z component is pointing in the opposite direction, so they cancel, so we ignore the z component. So it's just 0. Let's look at the y component. There is this segment. It creates an electric field in that direction. We took the yz projection, which is in this direction, which has a y component pointing in this direction. And the y component is given by sine of theta is the projection, sine of phi is the y component. So that is basically what we did. So we have the electric field, whatever its magnitude, then we multiply it by sine theta to get the projection on the yz plane. And then we multiply it with sine phi to get the component in the y direction. Cosine phi will give me the component in the z direction, sine phi the y direction. So we just substituted it. Well, dE is just this expression over here. Sine theta is just r over L, and we have the sine phi. And we made the simplifications. We took everything that is a constant out of the integral, so we are left with this integral. Well, the next thing is to identify the phi component, the phi axis. Now, we have to identify dq and also sine phi. Now, what I did, so again, this is the z-axis, this is the x, this is the y. I take this segment over there. It sees a very small angle, which I call the d phi. So the length of that segment is just dl. If I call the length as dl, the total charge in that segment is linear charge density, charge per unit length, multiplied by the length. What is that? The length of that very small segment is just the arc of a circle, and the length of an arc of a circle is just the radius of the circle multiplied by the angle it sees, r times d phi. And the linear charge density, we are already told that the total charge is q, the length is pi r, this is the linear charge density. So the charge of that segment is given by q over pi times d phi. Phi is positive, d phi is positive. So as I go over the segments, I should make sure that phi increases. Then I'm back here, ey. These are all the constants that I took out. Q over pi is also another constant I take out of the integral. What remains is d phi times sine phi. And so now I need to determine the values of phi. You see, this is again my ring. I take d phi, I take a segment over here. It creates an electric field whose projection on the yz plane is in that direction. As I change my segments, this is how the electric field direction changes. So it is pointing upward, that is for sure. It starts from 0. This is the z-axis. At this segment, it is pointing in the z direction. So phi starts from 0, and then it goes up to pi. So that's now 0 to pi. My mistake before was I was writing the angles corresponding to the segments of the ring, not to the direction of the electric field. That is why in first attempt, I said that phi should be negative. But since here we are summing over the directions of the electric field, not of the charges, phi is positive and it goes from 0 to pi. And that gave us the final result. Now let's continue. There is 2 more parts to this question. It says that what is the total electric flux passing through a spherical surface of radius 2r? This is x, z, y. This is my ring. It has a radius r. Now we imagine a Gaussian surface whose radius is 2r. What is E dot ds, dA, over this closed surface? Yes? Q enclosed over epsilon 0. What is Q enclosed? Q, the total charge. Done. And then the last question, D. This is my configuration. And we put at this point, no, not at that point. We put at this point an electron which has a mass m and a charge minus e. And then it is released. What is the initial acceleration? Well, what is the acceleration? Force over the mass. Well, the force is minus E times the electric field over m. This is minus E over m. The electric field has an x component and a y component. So the acceleration is minus E over m. Well, let's say what was the x component? This much in the I direction plus, and the y component is this much. So let's simplify it a bit. Minus E over m. Well, let's take about 1 over 4 pi epsilon 0. Let's take q over x squared plus r squared to the power 3 halves. This is L cubed. Now what remains inside is x in the I direction plus 2 over pi r in the j direction. This is the initial acceleration of the electron. Don't forget to use the vectors. In the question it is already stated that use the vector notation. Well, you see, the problem with using Gauss's law in such a problem is the electric field is, in general, you don't know any component of the electric field. So this function over here is unknown. But without knowing anything about this electric field, I mean, you cannot integrate an unknown function. So in the examples that we had discussed in the classroom, we first said that, okay, the electric field we can write in terms of one parameter only. And then we chose a surface. We claimed that, at least in the examples we had discussed, we could identify a surface over which that unknown function was constant. So we could take that unknown function out of the integral, and we could evaluate what remained. So here, in this question, can we write the electric field in terms of some function, some single function? Can you identify a surface over which the electric field is constant in magnitude, at least? If you cannot do this, then you cannot use the Gauss's law to obtain the electric field. So in this problem, it's kind of hopeless. The Gauss law is still correct. You see here, the Gauss law does hold for this red surface. The integral of E dot dA is still the Q over epsilon 0. But we just cannot use this equation to obtain E. Well, it's not so easy to imagine. Well, it's... Okay, let me go here. I already have the 3 axes. Or let me go here. Okay. So let's say maybe to that corner. The x-axis is this line. Okay. The y-axis is this line. The z-axis is over here. Okay. Now there is a segment, let's say in that direction over here, and which creates. We are looking for the electric field. By the way, at this point, this is my point P. Let's say this is my point P. Now there is a segment